In this topic, we are going to cover direct syscalls. But before we do, let's first have a quick primer of assembly. Assembly is a low-level programming language. At the lowest level, we have machine code, which is just a sequence of bits that our CPU hardware can understand and action. It's not really feasible for most people to create complex programs directly in machine code. So programmers abstract detail away by moving higher up. And the next level up from direct machine code is assembly. Assembly enables you to work directly with registers and perform interrupts. And each line in assembly usually translates to just one processor instruction. And it's important to note that different processors use different assembly languages. So compared to C, assembly is a lower level programming language, but compared to Python, C is a lower level programming language. So assembly is even lower level than C, and C is even lower level than Python. And the real difference in this case is the level of abstraction away from direct machine code. And we will be using assembly to make system calls in this lesson via Python. So every native API call has a specific number that represents it, also known as a system call or a syscall. And these syscall numbers differ between different versions of the Windows operating system. And these syscall numbers can be verified directly with a debugger, or you can rely on public research and lists. To make a syscall, you need to move the correct number into a register, and then in x64, the syscall instruction will then enter into kernel mode. And with direct syscalls in assembly, we can completely remove any Windows DLL imports. Instead of NTDLL doing the work for us, we can just set up the call directly ourselves. However, when making a syscall, we need to set up some arguments on the stack, move the correct syscall for the operation we want to perform into the EAX register, then use the syscall CPU instruction, which will then cause the syscall to be actually executed in kernel mode. So let's switch back over to a virtual machine and follow these steps in Python. Before jumping in to the practical demonstration of this lesson, it's important to point out that this isn't a malware creation course. However, if you are trying to use the same functionality as the Win32 API and you want to avoid directly interfacing with it entirely from user mode, you can also leverage Python and the ctypes library to directly perform system calls. So let's do that by allocating memory within our process directly, using a system call, and avoiding the Win32 API entirely, including both kernel32 and NTDLL. So let's start by importing and defining some functions, constants, and variables again, and we can copy and paste these from the undocumented API lesson. Copy and paste. We can remove the virtual alloc component, also remove the kernel32 component, and we can re-add NT status. We can save this. Direct syscalls.py. And now that we have these constants defined, we can start looking at how we will actually perform our syscall. Syscall numbers vary on different versions and releases of Windows. So we will only be focusing on this specific Windows 10 version in this lesson. There are ways to dynamically resolve these syscall numbers or to debug NTDLL, but that's outside the scope of this lesson. If we go online, we can instead make use of this great resource by Juru from Google's Project Zero, which contains syscalls for most recent versions of Windows. Here, we can show all syscall numbers for the ntallocate virtual memory function, and as we can see, this syscall has changed across different versions of Windows. Based on the version of Windows that we are using in this virtual machine, the syscall number we are going to be using is 0x18 or 24 in decimal, because the function that we want to call is ntallocate virtual memory. So now that we know the syscall number that we are after, how can we actually use it? For this, we need to leverage assembly. In order to trigger the actual system call, we need to set up some values in registers and the stack in ASM, and then make the syscall instruction to enter kernel mode and carry out the operation mapped to the syscall number. Specifically, on x64, we want to do this. Move into R10, RCX, move into EAX 18, so this is our syscall number, perform the syscall and return. And this isn't an assembly course, so we won't go into detail on exactly what is happening here in assembly, but just know that this is how Windows under the hood will also execute a syscall for us when we are using the Win32 API. So how can we execute this assembly via C-types from within Python? Well, we need to tackle this with a few steps. First, we need to write our ASM as shellcode in order to execute it from within Python. Then, we need to put this shellcode somewhere in memory. Then, we need to update the memory for that location to enable execution. Otherwise, we will have an error if we try to execute code from a non-executable memory location. Then finally, we need to call it. Let's make our lives a bit easier by first setting up a function to verify if a call succeeded or not. Next, let's write our ASM. And as we saw in the Python 101 for Hackers course, using pawn tools, it's possible to write ASM directly in Python. However, I don't want to compile and install binutils on this Windows virtual machine, so let's instead use a debugger. For example, we can use x64 debug. We can download this. And now we can open it. And now that we have it downloaded, we can use x64 debug to write our assembly. So what we can do is we can start a sacrificial process like Notepad. We can attach to this process. We can right click, binary fill with nops. And now we have this space where we can convert our assembly into shellcode. And it depends a lot on the calling convention, but typically EAX will contain the return value of a function. So to test that our assembly process in Python works, let's first just move the value 5 into EAX, then return. If the return value is 5, then we know that this is working as expected. So let's right click, go down to assemble, and we can say move into EAX 5, return. And here we can see that x64 debug has converted our assembly into shellcode. So now we can use this. Let's create a buffer. And into our buffer, we can put our shellcode. So here what I've done is I've copied the shellcode B805000000C3, which corresponds into the assembly, move into EAX5 and return. And this is now in the buffer variable. And we can get the address of where this is in memory. And we can print this out. And we can execute this. Input, not pause. And now we have a memory address. And at this memory address, we should have our shellcode. So let's take a look in Process Hacker. Search for Python. And so our shellcode is in this page, which we can double click. And here we can see that as expected, at B08, we have our shellcode. B805000000C3. However, this shellcode is not page aligned, and the memory protection of this page is read-write. So that means if we try to execute our shellcode from this memory location, our script will fail. So first, we need to change the memory protection of our shellcode. And in order to change the memory protection of a page of memory, we can make use of the virtual protect function. And here we can see that virtual protect changes the protection of a region of committed pages in the virtual address space of the calling process. So let's make use of virtual protect to change our memory protections. So let's start by defining virtual protect. And pass in the archetypes. We have an LP void. We have a size T. We have a D word. And an LP D word as defined here. And we also can see the return type. If the function succeeds, the return value is non-zero. If the function fails, the return value is 0. And now that we have it defined, we need to know how to call this function. So we can see the first parameter here, LP address, which is the address of the starting page of the region of pages whose access protection attributes are to be changed. And the address we already know, which is our buffer address. Next, we have DW size, which is the size of the region whose access protection attributes are to be changed in bytes. So that will be the length of our buffer. Next, we have the new memory protection option, which can be one of these memory protection constants. And lastly, a pointer to a variable that receives the previous access protection value. And we can see that these memory protection constants are the same as what we've used before. So we can use page execute read write again, because this has the execute flag enabled. We can also create our old protection variable. which is a D word. And now we can change the memory protection. We can pass in the buffer address, the length of the buffer, the new protection, and a reference to store the old protection. We can also verify that we don't have any errors here, and we can execute this. And we can verify the protection in Process Hacker. And here we can see the memory protection for this page is read, write, execute. And this is where our shellcode is currently stored. So now we can execute it. And in order to do that, we can make use of cfunctype. And here we can see the definition. The return function prototype creates functions that use the standard C calling convention. And here we can see the inputs. The first input is the return type, and then we can enter optional argument parameters. So let's set up our function. We expect a number as the return type, and there are no input parameters for our ASM, and we're only expecting 5 as a response. Now we can create our function based on the address of our shellcode. And now we can call this function and take a look at the output. We can execute this. And here we can see, as expected, we have 5 as a result. And we can change this return value here to be a 3, for example, and execute this again. And now we can see that we're returning 3 from our ASM. And we can also see what happens if we don't change our memory protection. And here we can see that now we receive an exception access violation because we're not able to execute our shellcode. So now we know how to get our ASM and call it from within Python. So how can we use this to actually create our syscall? So the first thing that we need to do is we need to convert our assembly here for our syscall into shellcode. And we can again use x64 debug for this. So we can press space, move into R10 RCX, move into EAX 18, x18. Then we can perform our syscall. And then we can return. And so here again, we have our shellcode, which corresponds to our assembly. So now we need to create another buffer. Let's call it buff2. And into this buffer, we need to place our shellcode. And again, this is just copy and pasted directly from the output from x64 debug. And now we can follow the same process. We can print out our second buffer address. And we can execute this. Closing bracket here. Fix our protection. And here we have our new buffer address. And now we can follow that same process. Let's copy and paste this function here. However, this time we want to change the protection for buffer address 2 and the size of the new buffer, which is longer. We want the same new protection, execute read write. And now we need to set up the function for the syscall in a similar way as we did for the test ASM. So we can create our syscall type. And the syscall that we are emulating is nt allocate virtual memory. And here we can again see the same function definition that we used in the previous undocumented API lesson. However, this time when using cfunctype, we first need to enter the return nt status. And then we can enter the arguments. And these arguments we can again copy and paste from the previous lesson. Then we can set up the function. And now we are ready to actually make the call. And the way that we make the call is exactly the same as how we used nt allocate virtual memory again in the previous undocumented API calls lesson. So let's again copy and paste from there. We can take the handle, the base address, the 0 bits and the size, copy and paste. However, this time, instead of directly calling the function, we can instead call the syscall function. And we can verify that this works. And if there are no errors, we can print out the address of our allocation. And we can try to execute this. So I've made a typo when copying over my shellcode here. We missed one of these 0x00s. And now that we've fixed our shellcode, if we execute this, we can see that we've made our syscall allocation at this address. And we can verify this by again looking at our Python process. And if we look in memory, we can see that at our allocation address, we have 12 kilobytes of read-write executable memory, which is the same size as the allocation that we made. We can rerun this. This time, trying to create 24 kilobytes. And here we can see our allocation as expected using direct system calls. As we have seen in this lesson, Python and C types can be really powerful when used together. We were able to write ASM into memory, then change the memory protection of that location, define the location as a function, and then also call that function to directly trigger a syscall. Basically, we could use Python to make a Win32 API call without using the Win32 API at all. And you can use this same method and approach to make other Win32 syscalls as well. But that's it for now, and in the next lesson, we are going to cover execution from a DLL.